Hello, everyone, and welcome to ACS Webinars, connecting you with the best and brightest minds in chemistry, live every Thursday from Washington, D.C. I'm Michael David, and I will be your host for today's special broadcast, which is part of Chemists Celebrate Earth Week, and is being co-produced with the ACS Green Chemistry Institute. Today, we will be joined by Richard Venditti, who is the professor in the Department of Forest Biomaterials at North Carolina State University in Raleigh. Richard is going to demonstrate the potential of paper and pulp recycling as a renewable, biodegradable, and environmentally compatible solution that could offer a better alternative to our current single-use items. Our moderator for today is David Constable, who is the Science Director of the American Chemical Society's Green Chemistry Institute. David has held a variety of industry roles in energy, environment, safety, and health, focusing on influencing scientists, engineers, and decision makers responsible for chemical research, development, and manufacturing in the chemical, pharmaceutical, aerospace, and defense industries. And with that, I would like to turn it over to David to get today's presentation started.
Good afternoon, Michael, and thanks everybody for joining us today for this webinar. It's part of ACS's Chemists Celebrate Earth Week, and we really are excited to have Richard Venditti do this webinar. He teaches, as you heard, chemical process control unit operations of pulp and paper and environmental life cycle assessment at NCSU. He has a PhD in chemical engineering, so he comes very well prepared and speaks very knowledgeably about this topic. So without further ado, I'll turn it over to Richard.
Okay, thank you, David. I'm just going to start off by giving you a little outline of what we're going to talk about today. First, we're going to overview the paper industry, and then after that, I'm going to show you 3 or 4 examples of green chemistry in the paper industry. After that, we'll talk about paper recycling, and I'll show you a great example of how we can recycle and most efficiently use some of our paper products. And then finally, some cutting-edge stuff. Innovation and green chemistry concepts in the paper industry. And then finally, we'll summarize and we'll have a little discussion about paper versus plastic for single uses. Now, before I get started, I want to explain one of the main objectives of this talk, and that is to demonstrate that the paper industry uses in a very, very strong way the basic principles of green chemistry. And so you can see there the list of things that are incorporated in green chemistry, things like safe chemicals, prevention of waste, appropriate starting materials. And what I want to do is show you that the paper industry uses sustainable raw materials, sustainable processes, and produces green products that meet the requirements of these principles. So first, let's talk about an overview. People tend to think that the role of paper and the amount of paper is decreasing, but that's not the case. Paper is such an important part of society and all the human activities. We usually think about communication, but packaging is a very, very, probably the most important part of the paper industry right now, and growing, as we have the Amazon phenomena and people ordering at their house, getting small USB drives in 2-gallon boxes. It's incredible how much more packaging we're going to demand in the future. Tissue and toweling is a big thing. And then other things that you might not think of, hygiene and health products, filtration. And then we have dissolving pulps. These are used to make cellulose plastics and also other additives that you might not think of. In this slide, I show a screwdriver. Very interesting story. Hundreds of years ago, screws, bolts, and screwdrivers were all made out of wood. And we've evolved, and we've come back to a screwdriver with a handle that is wood-based. So these cellulosic plastics are very important in society. I also show an ice cream cone. A lot of people love ice cream. Cellulose is found in ice cream. Actually, cellulose gums are introduced into the ice cream to give that ice cream an airy feel to it, and it increases the silkiness, the creaminess of the ice cream. So paper and pulp products are everywhere in our lives. This just shows paper and board demand globally. And what you'll see is we're about at 400 million metric tons of paper per year. So what does that mean? To get all that paper, we use about 1 billion tons of wood. And we'll talk a little bit more about wood later. And then we also use 20 billion tons of water. So we use the water and we actually return it to the environment after we've cleaned it and processed it. But it takes a lot of raw materials. This slide tells you another story. And basically on the y-axis here you've got consumption per person for different countries. And what you can see is the United States is about 300 kilograms per person per year. And what you'll also notice is that the amount of paper and board that is consumed is directly related to the gross domestic product, or how much people make. And what you'll see down at the lower ends here, emerging countries like China and India are only actually consuming about 50 kilograms per year per person. And what's going to happen is these countries, as they emerge, are going to grow in their use and consumption of paper. What that means is a lot more demand for paper in the future. It's not going away. So our raw material, paper, has a great story. We need forests and we use forest products. We use wood to make paper. Now, forests are incredibly important to society. I'm not exaggerating when I say forests allow life on Earth to exist. With it, forests help filter our water. They actually help us produce food that we eat, and they also clean the air and allow us to breathe. Forests are huge. The sad story is, since the industrial age, forest lands have decreased by 33%. The good news is, if we properly manage forests, we can get a lot of the ecosystem services from them, and we can actually provide 2/3 of the wood that we need for industrial purposes. So if we're efficient with our forests, it's really good. What are some of the benefits of forests? Basically, forests provide an unrivaled ecosystem services. In other words, they store carbon, they purify water and air, they produce oxygen, they produce good, healthy soils, they're a climate buffer. There's one estimate, and that estimate says that the ecosystems, if you had to pay for them, approximately worth about $4.7 trillion per year. That's what we get from our forests. Incredibly important for society. We do manage forests very carefully, especially in the United States, but globally, we have certification programs, and their main goal is to protect the forest and the life that's around it. Water quality, biodiversity, wildlife habitat, all these things are included in certification. More than half of forest land is certified in Canada, Europe, and Scandinavian countries, and that certification is third party. So SFI and FSC, third party organizations, do that. In the United States, 97% of timberland is certified, meaning it's managed in the proper way, and it's also documented how well it's managed. In the United States, 29% is from the third party. But in general, people that use forest products are getting the fiber and the wood from certified lands that are managed very sustainably. The United States has a great story. Between 1990 and 2015, the amount of forested area has increased. Well, why are we losing forest land? The fact is that fire, pest, disease, invasive species, they're going to attack the forests and consume the wood in a wasteful way. So if we're not using it in general, we're wasting it. So it'd be much better to take wood and make products for society rather than have it destroyed by pests. In tropical countries and in many places in the world, we're losing forest areas mainly because the agricultural lands are expanding. And also, people are using the wood for burning and not replenishing it as they should. So here's one of my points. Any method to promote forests is important. So how do we promote forests? Basically, what we need to do is have valuable forest products where people can make money and a living off the forests. If we have that, then people are going to value the forests and promote the planting of land as forests, okay? The other option is parking lots, buildings, roads, agricultural lands, which are important to society, but we have to have a balance. Let's go back to the objective of the talk, and that was to kind of demonstrate green chemistry principles. And the first one I want to really emphasize is that the forest products industry, including wood and paper, uses a very appropriate starting material, sustainable, renewable wood, and we feel that the value in those products is going to motivate people to keep land and forests. That is key to the global health of our world. At this point, I'd like to ask the audience a question.
And I will step in for this. So we want to ask you how you feel about this statement. The paper industry is a positive influence in sustainably maintaining the forest land, and just get your level of agreement to that. And your choices are strongly agree, agree, neutral, disagree, or strongly disagree. Well, Richard, 45% of the audience agreed, 17% strongly agreed, 23% were neutral, and then 14 disagreed, and only 2% strongly disagreed. So with that, I will turn it back over to you.
Well, I think a majority of the people on the webinar do appreciate getting valuable products from the forest as a way to promote forest land. And there are some people that are neutral or disagree. And I think that there are issues with some forests. There's always room for improvement. But in general, we're doing a good job by using forest products. Okay, let's move on. Now let's just talk about green chemistry at work in the paper industry. What's going on right now that we feel like is green chemistry? First of all, let's just talk about a modern pulp and paper mill. These things are enormous. The capital cost is about $1 billion. Sometimes environmental permitting could take 5 to 10 years and cost millions of dollars without the certainty of the location of a paper mill. So it's a big deal. Most of the new mills are being built in Brazil because they have a very good forest plantations, and then also in Scandinavian countries where they're trying to develop bioeconomies since they're so rich in forests. When we look at that paper mill or a pulp and paper mill, we break it down into unit operations. Each one of these unit operations has chemical engineering principles and chemistry principles, and each one of them is an opportunity to incorporate green chemistry, and in most cases, green chemistry is involved in each one of these operations, but it's a very complex process. One of the reasons why it's complex is because some of those green principles talk about recycling, avoiding waste, maximizing reactions. Well, they take a lot of operations. You can't just have one simple operation that obeys all these green chemistry principles. One of the most important parts of the pulp and paper industry is the conversion of this hard, solid wood into liberated fibers that we can make paper. And what we do is we call that pulping. Pulping is a process where we put chips into a water solution that has active chemicals, sodium sulfide and sodium hydroxide for the most part. And those chemicals we added about 20% weight to weight on wood. And the chemicals, what they do is they actually are there to dissolve the glue inside of the wood. We call that lignin. It's a three-dimensional phenolic type cross-linked material, and it's actually found in the middle lamella in between individual fibers. We dissolve that with the chemicals, and then we have the fibers, and then we have also a lot of dissolved organics. So that's the process of pulping, very, very important to us. Now, this is actually a kind of overall schematic of the pulp and paper processes, and I'll start off in the top left where we have logs coming in. The bark is removed, and we use the bark for fuel, so that's not wasted. After the logs are debarked, we chip them. The idea is that we get a uniform width that allows the chemicals to penetrate the chips in a very homogeneous way. Those chips are added to what we call a digester, where we add chemicals to that digester. Time, temperature, the chemicals actually dissolve the lignin in the middle and dissolve some of the carbohydrates, and we get pulp and what's called black liquor. It's black because there's dissolved organics. The washing step right here actually separates the pulp that we're going to use for paper making and the weak black liquor that has the dissolved organics. And we'll follow the pulp here. The pulp gets cleaned and screened to remove some contaminants, and then what we do is we send it to a bleach plant, which will take light brown pulp and convert it into white fiber. So brown boxes, of course, don't use the bleaching process. Copy paper and printing and writings often use the bleaching. And then after we've prepared our fibers, they go onto a paper machine, and a paper machine is an actual marvel in itself. Paper machines actually have tens of thousands of data measurements and control loops. It's very commonly known that actually a paper machine, a modern paper machine, has more of data and loops than does a 747 airplane. So it's a very interesting process. And then we're going to talk about this part of the loop right here from the evaporated recovery boiler and caustic plant. Let's go back to the pulping operation. And what we'll do is we'll just assume that we have 1 ton of wood. I mentioned that we're going to put 20% by weight chemicals on that. After our pulping, what we're going to have is we're going to have our fibers and dissolved organics and our spent chemicals. So what happens is we get about 1/2 ton of pulp. And you might be asking yourself, okay, well, what happens to all the organics and chemicals? What happens with those is that they are sent to a recovery boiler. We've got about 1/2 ton of dissolved organics and about 20% ton of chemicals. And I will mention to you, about 100 years ago, all this organics and all these chemicals were simply dumped into the river. We're much, much better than that now, economically and environmentally. So now let's focus on the recovery boiler. So what the recovery boiler does is it's really a miracle. What that recovery boiler is doing is many, many things. These recovery boilers are almost 10 stories high. They're a marvel of engineering. These boilers, they actually take the organic material and they combust them in oxygen to produce heat. And I should mention that the heat and power that we produce is all renewable and is about 60 to 75% of the energy we need in a mill. Very, very important. We're using green energy here. The recovery boiler's got another couple interesting things. It takes the chemicals and at the same time it's oxidizing the organics, it's actually reducing the sodium and the sulfur to make new active chemicals. So we're oxidizing in one part of the recovery boiler and we're reducing in another. We're also in that same recovery boiler generating steam. And the other thing that we do is we collect pollutants. So a lot of particulate and gases we recover do not emit to the environment. The latest mills, the most modern mills, are taking this energy right here, combining it with hog fuel, bark, and other forest residuals that are maybe laid on the ground, increasing our energy. So now that's one part of it, the energy recovery. Now the second part is what happens to the chemicals. Well, we have a secondary loop here that actually takes the chemicals from the recovery boiler and converts them into the active chemicals we need for pulping. The remarkable thing about all this is that we are recovering 95 to 97% of all our chemicals. In other words, we're using that sodium atom 25 times. We're not just throwing it away after one time. We're actually reducing our chemical consumption by 25 times. Very, very good, economically and environmentally. That was one aspect of green chemistry, those recovery loops. Then the second one is the use of enzymes as a green catalyst in the pulp and paper industry. So we basically know that enzymes are catalysts that actually use this kind of lock and key mechanism. In other words, we design an enzyme like this one, this is xylanase, that specifically attacks a certain substrate. Now, the graph on the right, the red right here shows the brightness of the pulp. We're trying to target an 89.5 brightness for our pulp. And what happens is we had a mill trial where we started to apply this xylanase to our pulp before we bleached. Now, this is important because typically we use chlorine dioxide to bleach to a certain brightness. Unfortunately, we discharge that chlorine dioxide after we use it, but we want to either eliminate it or minimize it. And using the enzymes is actually a very green chemistry way to minimize that chlorine dioxide. So what we did here was we started the mill trial, we added enzyme, and here is what happened, and then here's our brightness. After the enzyme, we start to decrease the chlorine dioxide. You can see that we can decrease chlorine dioxide by about 25% just through the use of this green enzyme. And then what happens is we stop the trial at the mill, and then the chlorine dioxide needs to go up to maintain that target brightness. So here's a great example of using enzymes as a green catalyst for our pulp mill. Now, the third example of green chemistry is the biorefinery concept. A modern pulp and paper mill, we've already discussed, produces paper and green electricity. What else can we produce? We can produce pulp, hog fuel, we can produce steam, turpentine, different oleic acids, fatty acids, rosin-type acids, and even more. We're creating vanilla, precursors, adhesives, surfactants, fertilizers, diesel, biofuels, and so much more. The new modern mills, that are being built and run in Scandinavia are producing lots of biofuels. You can see some of the numbers here that are wonderful, including CO2 emissions of minus 80%. Now I think I've tried to demonstrate some of the principles of green chemistry in the paper industry that exist right now. Some of these are the chemical recycle loops, the biorefinery concept, sufficient in energy, aqueous-based reaction medium, and enzyme applications to reduce energy as a catalyst. So let's go ahead and ask the audience another question.
So our second question for all of you is, the cycles that were discussed with regards to pulping accomplish which of the following? Do they recover and regenerate chemicals, convert dissolved organics to heat and power, all of the above, or none of the above? To call this a runaway would be an understatement. 95% said all of the above, and the rest were kind of split between the two, or three remained here. So I'll turn it back over to you, Richard.
Okay, this is where I can compliment our audience as being really smart and attentive. Excellent. I'm glad everybody got that. We're using those cycles in a very efficient way. So let's move on. The next thing I want to talk about is our products. We're getting to the point where we're asking ourselves, single-use products, how do we best use those in the world? And paper recycling is a key answer to part of that. Let's just kind of think about how much paper we use and how much plastic we use. Paper, we're using about 400 million tons per year, and 66% of that's recycled. If we contrast that to plastic, we're using about 350 million, only 10% is recycled. So what I've done is I've sketched how much paper and how much plastic we use per year. So imagine that these sketches are actually lines of trucks from the nose to the tail, wrapped around the world, and that just demonstrates to you how much material we use. It's incredible the amount of material we're using. So it's basically 12 loops of trucks for paper and 10 loops of trucks for plastic. Now, how does recycling fit in? Now, if you think about it, for paper recycling, we're recycling 66% of all our paper. What that means is actually of the discarded paper, it's only now 4 loops. That's an incredible reduction. For plastic, it's 9 loops, which is a reduction, but not as significant. So this is why the paper recycling is so important to society. Now, if you look around in the environment, what you're going to notice is that cellulosic materials like paper, they degrade very rapidly. Plastics, on the other hand, no, they don't. They exist for very, very long times. And this graph on the left just shows you one example. Cellulosic materials within 30 days amongst microorganisms in the environment degraded at 100% or so. Polyester, maybe 3 to 4%. Basically, paper is biocompatible. When it goes into the environment, it becomes part of the environment by being incorporated by microorganisms. So the recycling that we do in the United States, how does that impact society? Well, one of the things that happens is it reduces landfill. So if you look here, back in 2000, let's say, we had 40 million tons of paper going to landfills. Now, because of the different ways we use paper and the increased recycling, what you'll notice now is that in 2016, we've reduced that by half, only 20 million tons of paper. And one of the major reasons is our increased recycling. This graph right here shows the difference between virgin container board and recycled container board. And basically, we've got a bunch of environmental impacts. And what you'll see is the brown is the virgin and the blue is the recycled. And you can see the blue has many, many reduced environmental impacts. Now, it's important to understand virgin fiber is critically important. In other words, we can't have recycled fiber unless we have virgin fiber. So I'm not saying eliminate the virgin fiber, but I'm saying that recycled fiber has another advantages. Now, why can we recycle paper? Well, the real reason is that paper strength comes from what's called hydrogen bonds. Cellulose and fibers have a bunch of hydroxyl groups on their ends, and what I'm showing here is the hydrogen bonds between fibers. When you have this intersection of fibers in this random paper sheet, those hydrogen bonds give the paper strength. And in fact, very interesting, paper is stronger than steel on a per unit mass basis. These hydrogen bonds are plentiful and strong. However, what happens is when you put the hydrogen bonds in water, the water actually disrupts the hydrogen bonds between fibers, allows the fibers to release, and then we have a very easy recycling. When we recycle the paper, all we have to do is add water, the fibers fall apart, and we can process them and make new paper. What this graph right here shows is that the fibers actually, they lose a little bit of strength. So this curve right here is the tensile strength of the paper making fibers. And what we see is that the paper loses about 10 or 15% strength, but really it levels off. And really we can continue to use these fibers over and over and over again if they exist. Now, what does happen is some people might say you can only recycle paper 7 times. Well, that's kind of a urban myth. What happens is that is based on an estimated yield of 85%. In other words, what happens is some fibers, they break during the mechanical actions, and roughly we have a 90%, 80%. It's different for different types of grades yield. And so if you kind of think about that 85% yield, then yeah, it makes sense that a fiber could experience cycles 7 times and then actually statistically probably break up. So let's talk about the story about boxes. Boxes in the United States are recovered at 93.8%. In other words, 19 out of every 20 boxes is recycled. Only 1 is discarded, an incredible high recovery rate. Now, why is that? Well, it's because the paper industry has an incredible supply chain. Basically, here's a beautiful graph about how we get fibers for boxes. In total, we have about 180 million tons of paper globally that are put into boxes. And then the products are used and then they're end of life, and then we recover about 80% globally. So we recover this and we lose about this much. And what we do is we add some new recycled material to that mix. So we get 150 million tons of recycled fiber and 30 million tons of virgin fiber. We always need that virgin fiber to replace our losses. And then we're back to our 180 million. It's an incredible story about supply chain. Now, how is paper recycled? It's very simple. It's a very green process. We take bales of paper, we put them in water into a pulper. The fibers, hydrogen bonds disrupt. And actually in the pulper, we remove large size materials through this screen at the bottom. Then we use centrifugal cleaning to remove staple and sand. We use screening to screen out large materials like plastic films. We use the concept of hydrophobicity. Many inks are hydrophobic, and what we do is we use air bubbles to float them out. Finally, we can do washing, where we can wash out very small particles like ink and filler, and then we use some bleaching and some other things, and we get our recycled paper back. Very nice, very compact, efficient recycling process. Here's an example of our recycling process for taking mixed office waste and making away from home tissue. And you can see that we start off with a parts per million of 10,000 of ink, and in the end, we only have 640. And here's a napkin that you might see at McDonald's. Copy paper is clean to 10 parts per million, so it's a little bit more complicated than that, more steps, but the same kind of issue. So now we've kind of covered recycled paper, a couple green chemistry principles that we've covered. We prevent waste, minimize hazardous products because using paper is biocompatible. We're using appropriate starting materials, that's recovered papers, and we have biodegradable products. So let's ask the audience another question. Mike, can you take it over?
Our third question for you all is the ability to recycle paper back into paper is mainly because, and here's the choices, adhesive in the old paper can be replaced with new adhesive, the fibers never lose their strength, the paper is held together by reversible hydrogen bonding, or the fibers are never broken in recycling. And again, another runaway. We have 91% of the audience says it is held together by reversible hydrogen bonding. So Richard, I'll turn it back over to you.
That's correct. Paper is held together by reversible hydrogen bonding. It's a wonderful thing. If you think about it compared to plastics, we don't have that hydrogen bonding in the same way. We can't just use water to recycle. So let's move on. Now I want to talk to you about a couple advances, some of the innovative and emerging green chemistry concepts in our industry. What I'd like to talk to you about is nanocellulose. Nanocellulose is actually taking those microscopic fibers and actually using mechanical action or acid hydrolysis to create nanostructures, structures that have widths in the nanometer range. Well, why is this important? Well, if you think about it, if we make paper, we're actually putting down random fibers. And to make a coherent sheet of paper, you need to have 5 layers of fibers. Now, a regular fiber coming out of a tree is about 30 microns in width. So that means in 5 layers, we have to have a paper of a thickness of 150 microns. Now, think about it. If we could make a film or a sheet of paper with nanocellulose, how thick would the paper have to be? Well, nanocellulose, let's just say, is 30 nanometers in width. If we need that same 5 layers, we can make a coherent film out of a 150 nanometer thickness sheet. That's an incredible thing, that we can make these coherent sheets with just 5 layers of this nanocellulose. The other things is it's biodegradable, it's biocompatible, it's got a crystalline structure that's important, it's got chemical hydroxyl groups that we like. All these things make it a very interesting starting material. Now let's just kind of see what we can do with it. On the right here, we have nanocellulose film structure. This is much wider than 5. And then we've combined it with a wax, a renewable bio-based wax. And then what you'll see is that we've got a little coating on the top, and we have it actually infiltrating our medium. Now, what we're doing here is we're showing water vapor transmission rate. One of the things that is for plastics has a great advantage over some of the bio-based materials. And here's polyethylene and its water vapor transmission rate. What you'll notice is that if we use our nanofibrillated cellulose and we combine it with some waxes, what we can do is get water vapor transmission rates that rival or are better than some plastics, mainly with renewable material. Here's another application for nanocellulose. If we think about grease-resistant and oil-resistant materials, what you'll see is that a lot of the products that we use currently have fluorine in them. So we have these PFOAs. They can migrate from the food into the food you eat. Or if they're disposed of, they can go into the environment. Now, the thing about these PFOAs is they're not biocompatible. They actually persist in people's body or in the environment for very long times. Now, what we can do is we can replace that fluorinated material with nanocellulose. And so here what we're doing is we're showing you nanocellulose material, and what we have is a grease and oil resistance test. And what we're doing here, Dr. Paul in our labs, is actually taking cellulose nanocrystals, combining them with clay and soy protein. So we've got some very, very green material starting and making this very interesting structure. And what you'll see here is that the result is we have extremely good grease and oil resistance without the fluorinated compounds. In this section, what I wanted to show you was that we're minimizing hazardous products, we're using safe chemicals, appropriate solvent, great starting materials, and we have biodegradable products to serve society and give us products we need. Okay, so now I'm going to summarize. The last thing I want to do is kind of compare paper versus plastic. One of the LCAs that I'm going to use, life cycle analysis, is this one with paper plates and cups. And what we'll focus on are the cups. Now, what you see from the results from this, some of the information that I put together is that paper or plastic for single use, there are pluses and minuses to using paper. Let's go through some of the pluses. Paper is recycled at a high extent. There's a vast infrastructure for recycling. The economics of recycling are better. Paper remotes forests, plastics do not. Paper degrades in the environment. So lots of different pluses. But then when you look at the life cycle analysis, in the production of paper, the total material in that product is 2.5 times greater. So a paper cup is heavier than a polystyrene foam cup. What that means is that we need a little bit more raw materials, and when we have waste in the landfill, it's 2.5 times heavier. So that's a minus. Global warming, paper is a slightly less than that, and we're getting better in the paper industry at that all the time. Water use is higher for paper. Fossil energy is about equal. That is for the overall recycling and the whole life of the paper. Paper uses a larger fraction of renewable energy. I consider that a plus because we're using wood, promoting forests. Plastic is less expensive in general, and people like plastic. You've seen those commercials with the guys holding 200 plastic bags at one time. It's amazing. So they've got great properties. There's pluses and minuses. We feel that paper is extremely green. Okay, so let's do another poll of the audience. Mike, can you take it?
Final question for all of you. The next time you go to the grocery store, which would you prefer to use? Would it be a paper bag, plastic bag, or a reusable bag? %78 said reusable bags, 8% said plastic, and 14% said paper. So with that, I'll turn it over to you one last time.
I think what it's telling us is the group is very interested in reuse, which is a smart thing. Okay, so just kind of to summarize, paper has some advantages over petroleum plastic type products, and that is renewable and biodegradable. Petroleum also has some advantage, so there's pluses and minuses both ways. In general, recycled paper has better environmental performance than virgin, but they're all part of the same life cycle. We really need to think about the whole system and the life cycle. Another thing I want to leave you with is paper products consume wood and the associated lands to grow it. We believe that this is good. This is important. This encourages more forests. It allows people to live off the land with forests there. That can be an issue if wood is not sustainably sourced, but much of the world is sustainably sourcing wood. And then finally, the whole life cycle of paper is very important. Manufacturing, end of life, even the raw materials, and everyone needs to consider both the entire life cycle for paper and plastic. And so what I want to kind of conclude with you is that I've shown you some green chemistry principles and the paper industry, and I hope I've demonstrated to you that the paper industry is working very hard and is very successful in applying those green principles to the industry. I will thank the audience and turn it back over.
Chemists Celebrate Earth Week isn't officially over. ACS local sections, schools, businesses, and individuals are invited to participate in events in their communities with the common goal: communicate the positive role that chemistry plays in the world. Discover more at the link on your screen or in the chat. The 23rd Annual Green Chemistry and Engineering Conference and the 9th International Conference on Green and Sustainable Chemistry will be held together from June 11th through 13th, 2019 in Western Virginia. You can join us at this unique event by registering at the link you see on your screen. And with that, I'm going to turn it over to David to take our first question.
So I just would like to encourage everybody to make it to the 23rd Annual Green Chemistry Engineering Conference. We're very excited about the theme this year about closing the loop. There's a lot of opportunities in green chemistry to apply to closing the loop, some real problems. Richard, as you may have guessed, there's quite a few questions that have come up during the presentation. I'm going to try and group some of these so that we get as much covered as possible. There are a lot of questions around recycling. How much of what we throw in our recycling bins actually gets recycled? You know, many people say the recycled materials end up in dumps and not recycled. So can you talk about recycling paper and how much paper actually gets recycled? And a companion question to that is that with recent reductions in places to do recycling, how has that impacted the whole recycling industry?
Paper that's put in recycling streams basically gets recycled at 100%. There's very little that is not recycled. It makes economic sense for recyclers to divert things from the waste, and they can get from anywhere from $50 to $400 per ton for recovered paper. The economics are there for recovery. I'm not an expert in all materials, but I've heard that, like glass, for example, the cost to transport it and the value that they get from the glass and the process that they have to go through doesn't really enjoy the same benefits economically that paper does. And I've heard stories where glass is just either refused or not recycled. So that would be my comment there.
Great, thanks. There are a series of questions around paper, as you've pointed out, is coated or it is contaminated with other things. So for example, if you use paper for food, it will get contaminated with grease. Paper that is like a magazine cover has, a very shiny cover to it. And so what kinds of things are able to be done for paper, with that kind of contamination? Can it be recycled? What are some of the challenges?
So like food type containers that have a lot of heavy plastic coatings, they cannot be recycled in that same simple recycling system that I showed. Those are either discarded or they can go to specialty recycle mills. And those specialty recycle mills will have a separate pulper. They'll use more temperature, more time, higher shears, and maybe some sodium hydroxide and some other chemicals to help disperse them. But in general, if it has heavy, heavy plastic, the water can't penetrate and break those hydrogen bonds and it's not recycled. Things with grease, it's just a lot of our boxes come from grocery stores, and the grocery stores, some of them have wax boxes, some have a little bit of grease. The paper recycling operations can handle small amounts, let's say 1% by weight of grease or something like that. But if it gets inundated with batches of just grease and wax coated things, it won't be able to be worked. Things like magazine covers that have clay coatings with latexes, no problem to recycle them. We just have to pulp them and make sure that the coatings are dispersed.
What is the potential for using more paper-based products for food delivery and that kind of thing? So frozen food applications or other applications with food.
Okay. So I tried to show a couple examples where we're using nanocellulose, we're using biopolymers like protein and starch, we're using clay. If we can combine those in a very clever way, we can replace fluorinated materials. These fluorinated materials, if you put them in the microwave, lots of heat, lots of oil, lots of grease, a lot of transfer to your food, it's very important to society. I think that we're breaking through on some very interesting nano and non-nano solutions to food packaging. So you're going to see more paper straws. You're going to see more paper contained water. I mean, it's a no-brainer. Why not contain paper and water in paper? So you're going to see a lot more of those things. There's high potential.
So there's someone with a little bit of understanding of the paper making process. And so the question is specific. Are there any chemicals in the paper process like wet strength resins and similar materials that could be replaced with more environmentally friendly products?
So wet strength additives are reactive additives that are cross-linked. They give the paper wet strength. So you'll see them in soda carrying cases and beer carrying cases. And yeah, there are potential replacements. So, the wood industry has tried to move away from phenol formaldehyde. Same thing with the paper industry. Some of these cross-linkers are being replaced with reactive starches, proteins, nanocellulose, and other different things to impart temporary wet strength, but enough wet strength to maintain the paper through its use phase.
A couple people brought up a similar issue around the recycling paper process, and that is that in making paper initially, you use like the waste bark for green energy, and you pointed that out. But what about in the recycling process? Because you really don't have access to those kinds of materials. So what is the energy and the opportunity for greener energy approaches, because you have to dry the paper and so on and so forth?
Exactly. So the virgin paper has the black liquor that's available for heating and steam and energy. And in recycling, we don't have that. We rely on electricity from the grid in some cases. In other cases, we purchase natural gas and we run turbines and actually produce the electricity and have boilers, and we produce the steam. Now, just like any other industry, those gas-fired boilers, we could replace them with biomass. The issue with biomass is some of these recycling plants are closer to urban settings, and the amount of biomass and how you store it, it's just simpler for smaller recycling operations to use natural gas and other types of fuels. So definitely that's a place where paper recycling can improve.
So there was a number of folks that were interested in, the sourcing of trees and wood and so-called forester's paradox. The way to ensure long-term stability is to extract value from them, but you can counter that argument with, you're replacing a certain amount of forest diversity. So how does one manage that paradox?
The amount of commercial timberland and plantation is a small fraction of the overall forests in the United States and Canada and other countries. Basically, we have lots of forests in government parks, and actually those government parks are actually suffering from wildfires and things like that. So to not manage forests is not good. To overmanage more than what we need in forests is not reasonable. Nobody's going to do that. I think we have a pretty good balance of managed plantations versus natural forests. In general, we've got to promote wildlife diversity and things like that. But as we compare forests to parking lots and some of the alternatives that people might put land into for value, a managed plantation is actually a pretty reasonable and good place, and they're very well and sustainably managed.
So one of the things that I don't think you talked too much about was lignin. So lignin is many times burnt for its energy, but can you talk about some of the ways in which people are thinking about use of lignin?
Lignins typically are burnt, and we get some fuel value out of that in our recovery boiler. We need that to run our mills. However, oftentimes there's excess lignin. There's special lignins that are produced, and currently right now, there are some specialty mills. I'd say it's only 5% of our industry that are making lignosulfonates, and those are basically sold as surfactants and adhesives and other applications. That lignin is soluble, and we have really great uses for it. Now, what's kind of new is we have craft mills, and we have one here in North Carolina that are actually harvesting the lignin. So they acidify the lignin to make it precipitate, and then they press it and they wash it. And those kinds of lignins are going to be used for higher valued products, things like adhesives. And we have some research programs going on at NC State to replace things like phenylformaldehyde adhesives and put lignin in there as the adhesives, and lots of different other applications that are emerging from lignin.
A couple people brought up contaminants from paper making, like PCBs in wastewater or in the recycling process. There are these clays and other chemicals and materials that come out of the recycling process. What happens to those materials?
All mills treat their effluents, and their water effluents are either treated in-house or they're treated using municipal water treatment plants. Typical craft mill will have screens to screen the water. Then there will be primary clarifiers to remove almost all of the suspended solids. And then after that, we've got biological treatment, where we might use aerobic activated sludge type processes. And what that does is it reduces the organic material in there, BOD and COD, and the bugs eat the organic material. A lot of mills will have holding lagoons where the biosolids from the microorganism treatments settle to the bottom, and then we have finally clear water. That's virgin mills have that. Recycle mills, typically, they will have a clarifier system. They might remove BOD, or they might send their water to city treatment plants to have them treated.
Everyone recently has become more concerned about impacts of plastics to ocean environment. And the question was, do you see any analogous type of concern from the paper industry in the ocean environment?
So one of the research projects I'm doing is looking at actually microfibers that come off clothes when you wash them. And basically, it's a very similar comparison. What we get is a lot of the microfibers are polyester, and a lot of the microfibers are cotton or cellulose-based, cotton or rayon. And what we find is we've done experiments with ocean water, and we see that the cellulose-based materials degrade relatively rapidly in the ocean waters. Polyester, basically, it's inert. It does not degrade basically at all in the ocean. So cellulosics in general, when they do find their way to rivers and lakes and oceans, degrade pretty rapidly with very moderate environmental conditions. The paper industry does have some pollutants. The bleach plant effluents are treated and then discharged. The paper industry is working very, very hard to reduce chlorine dioxide, and an enzyme application was one that I showed you. Where we've come from, we're doing a great job with those water pollutants. PCBs, somebody mentioned. PCBs are really non-existent in the paper industry at this point. We had some serious problems with them when we had carbonless copy paper. And back 40 years ago or so, we just didn't understand the effect of PCBs in the rivers. That's all stopped.
So you know that there's been a lot of concern about PFAS in the environment, and there's this trend to be using a lot of those kinds of coatings in paper. You brought up some examples of newer coatings. How quickly do you think those kinds of newer coatings are going to be adopted?
Oh yeah, I think very quickly, and especially with food contact. I think when people start to think about their health and how disposable containers contact food and the oil transfers some of these materials. I see paper companies and paper chemical suppliers to the industry working really, really hard and effortlessly to make some of these replacements work. You'll also start to see maybe some old-fashioned type of technologies. We have glassine paper where we can actually press the paper to such an extent to remove pores and prevent liquid penetration in many ways. And I believe that we're going to see a lot of the old traditional types of making cellophane and things like that, saran wrap, be combined with some newer technologies like nanocellulose, and we're going to rapidly see changes in the next 5 years.
Thank you for watching this presentation. ACS Webinars is provided as a service by the American Chemical Society as your professional source for live weekly discussions and presentations that connect you with subject matter experts and global thought leaders concerning today's relevant professional issues in the chemical sciences, management, and business.